welcome video for my Algebra 3 prerequisite chapter number 2, in which we're going to continue our exploration of exponential expressions, but specifically scientific notation. So you've probably seen scientific notation before, at least heard that term, and what we use it to do is write really big or really small numbers as I guess you could say numerical factor A times a product of tens, several tens, okay? Where the absolute value of A is greater than or equal to 1, less than or equal to 10. Basically, we could say that this number A here, whether it's positive or negative, basically is a number between 1 and 10. So you could say, anywhere from 1.00 all the way up to, but not including 10, so like 9.99. We don't usually want to go over that and have two decimal places. We say n is an integer. So consider if you were to take a number A times 10 several times, then you would get a number that's many times bigger, but basically all you're really doing is shifting the decimal. So for instance here, I've given a couple of examples, but we say 6.4 times 10 to the 5th. Really all this means is 640,000. The reason why is because if you were to take 6.4 times 10 5 times, okay, you'd really just move the decimal 5 times to the right. And you can see that the decimal used to occupy this spot right here, but if we count 1, 2, 3, 4, 5, it moved 5 places to get to the end of the number, whereas also, if we were to look at 2.17, say, which is a number between 1 and 10, we could say times 10 to the negative 3. Remember that 10 to the negative 3, that's the same thing as 1 over 10 to the positive 3. So if we were to take a number times this, really what we're doing is we're dividing by 10, or factors of 10. So really, when you divide by 10 in the decimal system, you're really moving the decimal places to the left. So 2.17 times 10 to the negative 3 really is equivalent to saying this, because all we've done is we've taken where the decimal was located previously, and that 2.17 is right there between the 2 and the 1, and we moved it 3 places to the left, okay? So let's go ahead and use this idea of all I want to do is check to see that we can expand a number and rewrite the decimal in expanded form. So a couple of scientific notation numbers here. Notice we have negative 2.6 times 10 to the 9th. Of course, our numerical factor, its absolute value, which is 2.6, is between 1 and up to, but not including 10. So we would say that if I were to rewrite this in expanded form, we're multiplying times 10 to the positive 9. One way to look at this is if your exponent is positive, you're just going to move your decimal to the right. So we say negative 2.6. Now I'm going to write negative 2.6. And I'm really just going to do this 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to draw, let's put in our decimal right here. I'll draw a little arrow there. And all of these spaces that you see here, what we're going to do is we're just going to populate them with zeros. So really, this number is just a very, very, very big number that we were able to write very concisely in scientific notation. Counting backwards, we could see that this is definitely in the thousands, millions, billions, trillions, okay? So this is really the same number. And also this, we say 3.017 times 10 to the negative 6. We could say that all I'm doing is dividing by 10. So if I, again, I write this out 3017, we say that our decimal formerly located here would have moved 6 places to the left if we divided by 10 6 times. So we got 1, 2, 3, 4, 5, 6. Now there is one thing that I'm going to point out here. I'm going to put this decimal in. I'm going to put in a blank spot for all of these places that we're going to populate with zeros. It is most appropriate when you have a small number like this to put a 0 to the left of the decimal, okay? That way we know that there is a decimal there, all right? So equivalent statements here. That's pretty simple to do. It is converting from the decimal to scientific notation that tends to lose people, okay? So I'm going to go through a couple of examples of how we would take a very large or very small number and rewrite this in a scientific notation, and you can see that the breakdown of how to do this is listed here. So we say write the number in the form a times 10 to the n, where n is a counting number. We say, well, let's do this. We say determine a, which is the numerical factor. Now, the thing to remember here is this. A is some number that can be 1.00 all the way up to, like, say, 9.99. But we say what we're going to do is determine that numerical factor, and we're going to move the decimal point in the given number to obtain a number whose absolute value is between 1 and 10, including 1. So basically what I just said is we want our number between 1 and 10. So when you look at both of these, say, expressions down here, I'll give you the trick here. What we're going to do is from left to right, you're going to find the first non-zero digit in the number. So for instance, with this really big number here, I notice that the decimal is currently right here. I'm going to draw a little arrow at the first non-zero digit, which is this 5. 5 is the first digit that's not 0. I'm going to put a little arrow to the right of that. Now looking at this expression over here, I have lots of zeros. This is a very small number. But if I were to trace this to the right, the very first non-zero digit is a 6. So I'm going to put a little arrow right to the right of this. And the reason why I'm doing this is because when I rewrite this in scientific notation now, my numerical factor is going to be this instead, 5.21, and I'm going to put the decimal where I located our arrow here, okay? So for instance, this guy over here, it's going to be negative still, but I'm going to say it'd be 6, and then I'm going to write 0.893. Now typically I would recommend going out 2 decimal places, but it's okay to go out 3. This is certainly a number that is between 1 and 10. So now all we need to do is determine, well, what are we taking this times? 10 to the what? Okay. Now, the way we're going to determine this, it's exactly what this says here. It says determine n, which is the exponent on 10 to the n. It says the absolute value of n is the number of places the decimal point was moved. The exponent n is positive if the decimal was moved to the left, negative if the decimal was moved to the right, and 0 if the decimal was not moved. So looking at these expressions, one good rule of thumb is essentially this. I mean, we're going to count how many places it moved from where it was to where we moved it, which was between the 5 and the 2 here. In this case, we moved it 1, 2, 3, 4, 5, 6, 7, 8, 9 places. The question really becomes, though, should this be a positive or a negative 9? I'm going to say, well, this is currently a positive 9. One big reason why, no pun intended, is because this was a very big number. You know, to get that number back, you're going to have to move your decimal place 9 places back to the right. But another way to look at this is you always count from the arrow that you put in here to the decimal. I counted 9 places, but to the right, and I associate right with being positive, whereas if I were to look at this here and I say, well, how many places did this move? We have 1, 2, 3, 4, 5, 6, 7, 8. So we moved 8 places and we moved it to the left. I counted from the arrow to the decimal and I counted to the left. So what we're going to do is we're going to use these properties of exponents that we've explored in the past to really kind of deal with scientific notation operations. So when you look at this here, we say, okay, use the properties to perform the indicated operations. Basically what we're going to do is we're going to say, well, multiplication, it doesn't really matter what order we do it in. So the first thing we tend to do is multiply these 2 numerical factors in front. So let's say 5 times 7 here. Well, 5 times 7 is 35, so 5 times 7.1 is going to be 35.5. So I get this here, and you'll notice that next what I'm going to do is I'm going to take 10 to the 5th times 10 to the negative 7. Now remembering our rules of exponents, 10 to the 5th times 10 to the negative 7 is going to be equal to 10 to the 5 plus negative 7, which is 10 to the negative 2. So I get this right here, 10 to the negative 2. And the other thing I want to point out here is this, well, essentially, I'm not supposed to have 35.5. I'm technically supposed to have some number between 1 and 10. So what I'm going to do is I'm going to rewrite this again as 3.55, and you'll notice that our decimal moved. Now, which way did it move? Okay, because this is going to make a difference here. We had negative 2 to begin with. If I count from the arrow to the decimal, okay, you'll notice I counted 1 spot, but to the right. So what I'm going to do is I'm going to add 1 onto the negative 2 that we currently had there. And we're going to say that this is the same thing right here. And likewise, when we divide things like this, we're going to say 1.2 divided by 3. You know, I can get a calculator out here. 1.2 divided by 3. We'll go ahead and do that. 1.2 divided by 3. We're going to get 0.4. Okay, so we get 0.4. 0.4 times 10 to the what? Now, using our rules of exponents again, we're going to say, well, a quotient rule says we're going to take the bottom exponent away from the top exponent if these have the same basis. So 10 to the 6 or 10 to the negative 3 is 10 to the 6 minus a negative 3. 6 minus a negative 3. So in other words, we get 0.4 times 10 to the positive 9 right here. Okay. So the last thing I want to do before we kind of finish this off is look at maybe a application situation. So let's go ahead and read through this. We say as of December 2011, the United States has spent $2.6 trillion on the wars in Iraq and Afghanistan. So we've got a source here. You can go look it up. But we say at that time, the U.S. population was approximately about so I'm skipping straight to scientific notation, 312 million. So the question really is here, if we were to, take the cost of these wars and evenly divide it among every single individual in the United States, how much to the nearest dollar would each citizen have to pay? So really this is just a division problem. And what we're going to do is we're going to take $2.6 trillion, and we're going to divide it by 312 million, which the nice thing is I've already kind of provided that here, or we've been provided with that information. So the 2.6 trillion, what we're going to do is we're going to rewrite that in scientific notation. And trillion, I want you to think about this. 2.6 trillion is really just this number right here. Bum, 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 bum. That's 2 trillion 600, billion, sorry, let's see, thousand, million, billion, trillion, no, okay. So 2 trillion 600 billion dollars. That's what 2.6 billion is. If we were to rewrite this in scientific notation, really this is 2.6, and a good rule of thumb here is a trillion is really just that times 10 to the 9th there. So what we're going to do is we're going to divide this up amongst all 3.12 times 10 to the 8th citizens. Say, well, how many dollars would each citizen owe, roughly here? So again, we're going to need a calculator, but we can do this in pieces. We say we'll take our 2.6 divided by 3.12, and we get this 0.83 repeating here. I'm going to go ahead and write that down. We say 0.83, and I'm going to say repeating for just the moment. And then using our rules of exponents, 10 to the 9th over 10 to the 8th is 10 to the 9 minus 8 is 10 to the 1, okay? So all I want to do is I want to readjust this here and say, well, really, I'd rather have this be a number between, 1 and 10. So the first non-zero digit's 8. We'll put the decimal right after that. I get 8.3, and I'm going to say 33 repeating. And in this instance here, we're going to say, well, I already had 10 to the 1. If I count now from the arrow to the decimal, we moved it one spot, that decimal, but I counted to the left. So really, I would say, well, I'm taking 1 away, and 1 away from what? Well, from the 1 that was currently here, so I get 10 to the 0. Another way to write this actually would be 8.33 repeating, and we'd say everybody owes about $8.33 if everybody can pay. But, not everybody can pay $8.33. Cheers.